So this is the second part of other common functions. Sketch the graph of the function f of x equals negative 1 over 2x. What I would like for you to do is recall this function, 1 over x. It looks something like this. Well, because of this negative, this graph will reflect over the x-axis. That's why it's going this direction instead of this direction. So it's reflected over the x-axis. Because this is the same thing as 1/2 times 1 over x, remember if you multiply by a number that's between 0 and 1, it compresses your graph. So what I want you to do is imagine that you put your finger here and your thumb here, and you just squeeze together. That's what this is doing to the graph. It's compressing it. So that's why this looks a little bit closer to the origin here. It gets a little bit flatter, and also here. So it's compressing and it's reflecting over the x-axis. How about functions of the form a times x to the 1 over n? Now remember, this is the same thing as a times the nth root of x, which is also here. This tells you the index on your radical. So your parent function, f of x equals x, this is your identity function. We'll just compare it to that one. If you have x to the 1/3, that means the cube root of x. That's the same as the cube root of x. This will be your graph. Notice it's really similar to x cubed, except x cubed goes this way. Okay, so x to the 1/5 would be the same thing as the 5th root of x. And it looks this almost exact same shape. The only difference is how steep it gets this way and how close it is in here, how it kind of flattens out towards the y-axis in here. The next type of function we're going to look at would have even roots, like x to the 1/2 power. Remember, that's the same thing as the square root of x. This one's the same thing as the 4th root of x. This one's the same thing as the 6th root of x. This one may be a little bit easier to see the differences than the ones that had the odd roots on the previous page. This is your parent function, the square root of x. Notice how whenever you change this to the power of 1/4, or you change your index to a 4, this gets really, really close to the y-axis. It makes more of a curve here than before, and it doesn't get steep quite as fast. Whenever you start increasing that denominator, it continues to get less steep, and it gets even closer here to your y-axis. The absolute value function always makes this V shape. You can also look at an absolute value function as a piecewise function, which we'll be talking about in just a few minutes. So what if we wanted to sketch the graph of f of x equals -2 times the absolute value of x? Well, we know that we are going to have to stretch the graph. Remember, the absolute value function is this V shape. Both sides of the V go off at 45-degree angles. We need to stretch it so that it's taller and skinnier. So it's a vertical stretch. I'll just exaggerate it a little bit. And because of this negative, we know we have to reflect it over the x-axis. Of course, you can test a few points and make sure you've done everything correctly, but it would look something very similar to this. I'm so sorry about my dog barking. Okay, let's keep going. Oh, the greatest integer function. This one is just one of those really, really crazy functions. Sometimes it's better to see a picture than anything else. So let's take a number line, pretend like that's straight, with 0 here. Okay, I'm going to make a table of values. We'll just pick a few and see what happens. So greatest integer, first of all, these crazy brackets, it's like this with an extra little line in it. This crazy bracket is what tells you that it's called the greatest integer function. If I were to put in 1.5, it's the same thing as 1.5. 1.5 is here. Greatest integer function, if you had this greatest integer of 1.5, it would mean find the greatest integer just less than or equal to this number. Well, this number is not an integer. So what we want to do is get the one that is just less than that number. That would be a 1. So what if I actually chose the number 1? The greatest integer of 1, well, 1 is an integer, and I want the greatest integer just less than or equal to that number. Since it is an integer, then that's the integer that I want. So what if I pick a number in here, say sorry, that's not 1.5, say 0.5. What is the greatest integer just less than or equal to this number? That would be 0. So what if I pick 0 then? That one is an integer, so I just keep that number. So keep going down the number line here. What if I pick a negative 0.5? What is the greatest integer just less than or equal to that number? It would be negative 1. But what if I pick negative 1? Negative 1 is an integer, so I just keep that one. Let's do one more. Let's pick this one. That would be negative 1.5. What is the greatest integer just less than or equal to that number? The next integer down is a negative 2. So what happens when you graph something like this? You get this graph. Now remember, let's see if I can point here. When we put a 0 into our table on the previous page, we got 0. If you put in a 1, you get 1. If you put in a 2, you get 2. If you put in a 3, you get 3. So that's why we have all of these solid circles on each of the integers. But what if we put in a 1/2? It was still 0 because 0 was just less than 1/2. Well, what if we put in a 0.9? It was still 0 because 0 is just less than 0.9. But once we did get to this 1, it jumps up to this line. That's why it cannot exist here. Remember, you have to be able to do that vertical line test. If you do a vertical line test and this point is darkened in both of these places, then the vertical line would touch the graph in 2 places, and that can't happen if it's to be a function. So once we get here, we leave it open because it jumps up to this step. Continues along, jumps up to this one. Continues along, jumps up to this one. So this is actually the basic graph of the greatest integer function. So piecewise defined functions are functions that are, exactly what it says, defined in pieces. So this one is telling you what the 2 pieces are. For every x value less than or equal to negative 1, you put your x's into this part of the equation. For every x that's greater than negative 1, you put your x in here. So let's see if we can figure out a few points. Let's try x equals 2. Where does 2 fit? 2 is greater than negative 1, right? So we would put it in this part. 2 squared would give us 4. But what if we were to actually put a negative 1 in there? Where's negative 1? It's in this one because of the little equal to bar right there. So we would say negative 2 times this negative 1 minus 2. Negative 2 times negative 1 minus 2. That would be 2 minus 2, which is 0. So at negative 1, we get 0. Okay, tell me this. what would the other piece be if it could be -1? If this could be a -1 and we put it in here, -1 squared would end up being a 1. Now I put this little dashed line around it because we know it can't actually be that, because there's no equal to bar under here. So what if we pick the number -4? -4 falls into this one. So we would say -2 times -4 minus 2. That would be 8 minus 2, which is 6. So what happens when we graph all of these? I'm going to have to cover up my function for just a minute. If we were to graph these, we get the point 2, 4, and -1, 0 is on this one, and then we have -1, 1, which could be here, but that one's not really supposed to be there, and then we have -4, 6. As you can see, this is defined in different pieces. For x is less than or equal to -1, we have this straight line, which corresponds to this, which is linear. And then for x is greater than -1, we have part of a parabola, which is also true because we have an x squared here, which is a quadratic. So that side should be a parabola.